Hello again, PAOS 316ers. This is the second part of the T-test mini lecture. This time, instead of working with smaller numbers of observations where we're comparing two means, we are looking at matched pairs, our pre-posts. So here what we're doing is we actually have data and our observations, let's say that they're individuals, involve taking a measurement on an individual before something happens and after something happens. And what we're actually doing is we're saying, is there an effect? Is there a difference between the before and after? So what we're going to do is to make a hypothesis. We're going to gather our data, which is in two columns because we're looking at the difference between two variables. We're going to create a third variable where we calculate the difference for the before and after scores. We're going to calculate the average difference between these two columns. We're going to calculate the standard error for the mean differences. And remember, the standard error is just like the standard deviation, but for samples. We will calculate our t-value, and then we're going to check to see if our t-value is statistically significant on that same t-table using n-1 degrees of freedom and an alpha level of 0.05. So we're going to make our hypothesis, which is a little bit different from before. So our null hypothesis is going to be that our differences are equal to some hypothesis value that we'll call D. And a lot of times your null hypothesis is just going to be that the differences are equal to 0, which is just the same as saying that there's no difference between the before and after. With a one-tailed hypothesis test, your alternate test is that the differences are higher than whatever this value is, or that the differences are lower, right? So one-tailed is you have to choose a direction, either it's more or it's less. And for two-tailed, your alternate hypothesis is that, well, it's not equal to this value of D, or it's not equal, let's say, to 0. It's either higher or lower. We don't know what it is, but we're going to look for both effects. So in the example that we went over in class, I'd said that we're going to imagine that you Albany students, we took a measure of how much they drink per week before they received counseling about alcohol abuse. Then we collected data after the counseling on how much they were drinking per week. And what we want to do is to figure out if the counseling had an effect. So we're saying, is there a difference between how much you Albany students were drinking before counseling as compared to what they were drinking after the counseling? So our hypothesis is that the differences are equal to 0, that there's no change in drinking behavior after counseling. And our alternate hypothesis, which you'll notice is two-tailed, is that the differences are not equal to 0. And again, our rejection region is this yellow area. With a two-tailed test, we're saying it's either higher or lower. So we're looking for either a higher effect or a lower effect because we're not sure whether it would be higher or lower. If our values fall in this yellow shaded rejection region for the differences and our means, then we get to reject our null hypothesis in favor of our alternate hypothesis, which would be that the differences are not equal to 0. So we could have an alternate hypothesis if we were doing a one-tailed test where we said, well, if they're not, if there is no difference, then you Albany students would be drinking more, right? So the implication there would be that the program is actually causing students to drink more. And if we chose that test, then we would not be able to detect, because we're putting our rejection region over here in this higher area, we wouldn't be able to detect if the program actually resulted in or was followed by lower drinking on part of the students. Now we could have a different alternate hypothesis if we took the one-tailed approach that you Albany students drank less after counseling. And if we were focused on that, right, the implication is that the counseling was associated with lower levels of drinking. But if the program actually made students drink more, which would be over here on this side, we would not be able to detect that effect. So that's setting up our hypothesis. Our step 2 is gathering your data in two columns. And if you double click on the embedded Excel sheet, you'll see that we have a before column and an after column. This is a simple random sample of 100 students from UAlbany. and their weekly drinking patterns. So here, the number of observations that you actually have is 200, right? Because you have before and after. You have 100 subjects that you're including because we're only looking at 100 students and we've gotten 2 scores from them, one before and one after, but we have 200 total observations. The next step that you're going to do is to create this third variable we're going to call differences, which is just going to be the score for after minus the before score. So we would just type in, if I were to do this from scratch, right, I would just say the differences, this is my new variable, and it's going to be equal to the after minus the before. So just a simple function there. And then I would just drag that down. Now the values in this variable are saying whether or not the students drank more or less after the counseling, where the positive score indicates that they're drinking more, right? So this person before the counseling was drinking 2 drinks a week, and after they were drinking 4 drinks a week for a difference of positive 2. However, this person right here was drinking 5 drinks a week, and after we're only drinking 3. So that's a difference of negative 2. So your fourth step is to calculate the mean of the difference. So all you're going to do is to go in and use our handy dandy function for average. You're going to type in equals the average of all of the differences, right, of this new variable that you've created. And you'll see that the mean difference is negative 0.48. Step 5, excuse me, is to calculate the standard error of the differences, because remember when we're talking about samples, we talk about standard error instead of standard deviation. But the tricky thing is that in Excel, you're just going to use the standard deviation function for samples. So you'll type in equals stdev.s, and you're finding the standard deviation of the differences. So you would just highlight that column. And you would get a standard deviation of 4.15. In order to calculate your t-value, you need to know the average difference. We already calculated this. You need to know the standard deviation. We already calculated this. And you need to know the number of observations. Now, the number of observations here is just going to be the number of observations under our differences variable, right? So that would be the square root of 100. So what we're going to do is to calculate our t-value. If you just double-click right over here, we're going to calculate our t-value by taking the absolute value, and this is just so that we're not getting negative numbers, of the mean differences, and that's our numerator, and we're going to divide that by the standard deviation divided by the square root of 100. So you can see that formula right up here. We're taking the absolute value of our differences, and then we're dividing it by the standard deviation divided by the square root of 100. And that gives us a t-value of 1.159. The next thing that we're going to do is to check to see if our t-value is statistically significant on a probability table with degrees of freedom n-1. Now, why are we using degrees of freedom n-1? Well, we have over 30 observations, so we don't need to make an adjustment there. And we're actually only looking at the one variable. We're looking at the difference, the differences. So that's just one variable. We're not actually looking at 2 variables there. So we would just make an adjustment of n-1 to get our degrees of freedom. So if we go to our t-table, right, I told you that we had 100 observations. -1 is 99, but this table doesn't get as specific as we'd like it to be, so we're going to use 100. We were doing a two-tailed t-test with an alpha level of 0.05. So we would just find out where those meet, and we get a critical t-value of 1.984. So what we would do is we would look at our critical value, 1.984, and we would compare it to our t-value, which you'll remember was 1.15. And if your t-value is higher, you reject. But our t-value is actually lower than the critical value. So once again, we're going to fail to reject our null hypothesis. So we're saying we don't have enough evidence to say that drinking pre and post counseling changed. So if you want to look at that, you can see all of that detailed here on this table, including the comparison of our t-value of 1.15 and our critical value. The t-value is below the critical value, so we failed to reject, and the implication is that the counseling had no effect on students' drinking habits. So in Excel, what we would do is we would go and use that same analysis pack that I showed you how to put into your Excel file. And what you would do is on this table, you would go to data. So these are our before and after scores. I'll do it right here so that you can see. You would go to data, and you would go to data analysis, and you would choose the t-test, the paired two sample for means, because we're looking at paired two samples. So we would click on that, and it says put in the variable 1 range. So we would select all of the data under the variable 1 name, and then we would select all of the variables, all of the numbers under the after, our variable 2 range. Our hypothesized mean difference, again, is 0. We are going to have an alpha of 0.05, and we're going to press OK. This is going to output onto a new sheet your t-test, the paired two sample for means. And what we're going to do is just to compare that to what we found with our calculations. So what this actually does is it goes through and it calculates the mean and the variance for each variable. We didn't actually do that, so we're not going to compare that. We can look at our degrees of freedom, which are 99, which we knew from looking at our table. We see our t-stat is 1.15, and that matches with our calculation of our t-value. We can see that for two tails, our critical value is 1.984, and that is what we found on our table. And we can see that with this, even if we were using a p-value to test our hypothesis with a alpha value of 0.05, because our p-value for two-tailed is greater than 0.05, we would still fail to reject our null hypothesis. So that is the end of our second small mini lecture on doing t-tests with matched pairs data. One more left, which is looking at f-tests and f-distributions, and that will be up shortly. Thank you.